In this video, I'm going to be talking about waves, specifically traveling waves and standing waves. Part of the video will be computer simulations of how waves travel down lines. And part of the video will show some real-world demonstrations that were done with string. Whether it's a mechanical wave or an electrical wave, the same math applies, and so we see the same phenomena. Whether mechanical or electrical, both systems involve a signal generator, some transmission line, and some type of load at the end. Here I have a simulation of a voltage wave traveling down two types of materials into an open. An open means nothing's actually at the end of the line. If this were string, the end of the string is left unattached to anything. The first material is a high-speed material, and the second material is low-speed. We can see the wave is traveling about twice as fast through the high-speed material than the low-speed material. When we hit the boundary, we saw some energy reflect. When you transition from a high-speed material to a low-speed material, we see a negative reflection coming off. The polarity flipped. Since we're traveling through a different material, we also saw the transmitted wave change shape. Here's that negative bounce again. Notice the magnitude of the transmitted wave goes down by the magnitude of the reflected wave. This is because at the transition, the 1 volt that was going to the right had 1/3 of a volt going to the left subtracted from it. So we have 2/3 of a volt now going to the right. Now we're approaching the open. When the wave hits the open, we're going to see a reflection, but this time, because we're not transitioning to a different material, we're not going to see a change in the magnitude, and because it's an open circuit, we're not going to see a change in the polarity either. So there's our bounce, and it's going to travel down the line again. Now, when we transition from a low-speed material to a high-speed material, we're not going to have a polarity flip. So we're going to have a reflection. The reflection is going to be 1/3 of that magnitude, but it's not going to change polarity. So we're going to have a 0.22 volt reflection going to the right, and to balance things out, that means to the left we're going to have a 0.88 signal going to the left. So notice the high speed is about twice as fast, and when we went from low speed to high speed, we did not flip the polarity. Here we have more or less the same start to the simulation. I've jumped ahead to where we've already reflected off of that transition between the two different types of line, but this time we have a short circuit instead of an open. A short for a string would be if you tied the string down to a fixed point. And electrically it would be if you tied a voltage down to a fixed point like ground or 5 volts even. And here you see the flip happen. The magnitude didn't change, but we saw the polarity flip. Here we show what happens when waves collide. These waves are the same polarity and they'll add constructively where they meet. Therefore, when they meet, the 1 volt pulses will sum to 2 volts on the line. However, they don't have an effect on each other once they've passed through. Here we have a positive pulse traveling to the right and a negative pulse traveling to the left. When they meet, they still add to make 0 volts on the line this time. The actual pulses are not affected, just the voltage on the line. This is an experiment you can do at home or at a school. I've taken a heavy rope, tied it to a light rope where it's labeled soft boundary, and tied that to a fixed point, which acts like the short from before. The heavy rope is a slow material, and the light rope is a fast material. When I excite a wave on the rope, the first thing we'll see is a positive reflection at the soft boundary. At the fixed point, we see a negative reflection. The waves will keep bouncing back and forth, slowly losing energy due to friction. Again, a positive reflection when we go from low speed to high speed, and a negative reflection when we hit the fixed point, or the short. In electronics, any DC voltage is a fixed point and acts as a short for waves. This is a standing wave generator. Instead of a broadband short pulse, we'll excite it with one frequency at a time and let the energy build. The ends of the strings are maintained at a fixed point. At this frequency, the string is half a wavelength long. A wave traveling from the center and reflecting from the right travels 180 degrees. In that same time, the wave sourced by the generator on the left travels 180 degrees. When the reflection from the right meets with the generated wave from the left, the two signals are 360 degrees apart. They're in phase and add constructively. When the string is 3/4 of a wavelength long, the wave traveling from the center and back again after reflecting off the right travels 270 degrees. And in that same time, the generated wave from the left has traveled 270 degrees. So the two signals are 540 degrees apart. They are out of phase and add destructively. And this is true at every point on that line. When the string is 1 wavelength long, we can see a full sine wave develop, with the null at the middle. The string is 36 palms long, and the null is at the 18th. When we're at 1 1/4 wavelengths, the generated and reflected waves again are out of phase at every point in the line. Since they're out of phase, the waves cancel each other out. And when we're at 1 1/2 wavelengths, we can see 1 1/2 sine waves develop. We have 4 nulls now, each spaced 12 palms from their neighbors. And we have 3 peaks, again, spaced 12 palms from their neighbors. Now I'm going to show that we can model at what frequency these constructive and destructive interferences happen for a given string. This is Circuit Mason. It's a simulation tool that is typically used for electrical simulations, microstrip lines, amplifiers, capacitors, that sort of thing. It's easy to add new models in the code, so I've made a mechanical string model and measured the tension, weight, and length of the string from the previous experiment. This code shows what happens over frequency, instead of showing what happens over time like the previous simulations. This is a companion code which can calculate how big the wavelength is on a line for a given frequency. We measured the line to have a tension of ½ Newton, the string weighed 3.3 grams, and it was 65 inches long. For the measured data, we predict this line is 1 wavelength long at 9.6 Hz, since 1 wavelength is equal to 360 degrees. Here we have our predicted response over frequency. So at 4.8 Hz, we see a strong response should happen. At 9.6 Hz, we see a strong response will happen. And at 14.4 Hz, we see a strong response will happen. And we also see the nulls that we predicted at 7.2 Hz and at 12 Hz.